But it's a real pleasure to be back here at a nice conference. So I would like to thank the organizers for this and also for allowing us parents to be part of the conference while our children play. Yeah, so today I want to tell you about computation of integral theory. I will focus on M1 for bar, so the moduli of elliptic curves for marking, the number compactification. And the technique we use is something we call word tracking, and it goes by the geometry of alternative compactification. So this is done with Visa. And I wanted to start the talk by giving you like how we're contributing towards this panorama of moduli conference. So maybe we just try to give a non-extensive, non-deep panorama of moduli to the occurs and applications. Right. So, of course, when we talk about moduli spaces of curves, the remodel compactifications can therefore be in the most beloved and nicest possible compactification. But I want to push the message that may be interesting for various reasons, and I'd like to give an example to consider moduli spaces of more singular curves as well. So what I wanted to do was just to cite a few words and try to just try to give you a picture. So maybe the first reason that historically came up was to study the relational geometry of the living matter. So in particular, you could think of the question, well, we know that for high G or fixed G and high M, these spaces are general type, and so we might wonder what the canonical model is. More generally, you might wonder if it is possible to construct four or several spaces that at least the rational map on MGN, and whether all of them are themselves model. So there's a program initiated by that aims at studying the canonical model of MGN bar, and there is multiple reference so we started with what is called passive timing, so it started in sense even before we were super, very much from the perspective of GAP and the minimum model program. And then more recently, when going with alternate right. So these people perform the first steps in the key program. The first step is the Victoria contraction of NGN bar. And the Victoria contraction can be thought of as modular space of curves that admit cascadal singularities, so ordinary cusps of genus 1 that replace elliptic tails. And then what is these group of authors developed these techniques to study further the these two steps that are fixed and not much. Besides this general work in these first few steps of this program that are performed for general GNN, and then there are a number of works that respect the low genus situation, and in particular, SMILE constructed for species alternative compactifications of the space of elliptic curves with an arbitrary number of markings, and the geometry of these modular spaces is the one that I will try to describe, and I will try to convince you that once the geometry is in place and well understood, then we can use it to make computations such as this one very easy. Okay, and then there are a number of other works. For example, I work in school, and there's perhaps there is one work that I want to mention in this genus one line. This is due to Bossi and what they do is they classify. So they classify all the compactifications that we can find of the space of genus one curve that only use covalence singularities in the boundary. And it's perhaps interesting to know that the number of compactifications that you can find explodes very soon. So already for n equals 5, they are in the mid-ones. This is because there is, so the geometric complexity is not so much, as we will see, but the combinatorial complexity is much bigger. Okay, so this was for abstract first, and then there are applications to modular automatic curves. And this goes back to the people who were here on how to find it, but we say it started with work of and this part here. And very briefly, the problem now with the next sort of applications that I want to mention is if you consider modular spaces of embedded curves, so in the form of table maps, for example, and the third application I want to mention is modular spaces of differentials. So there are well-studied compactifications in both cases. For example, for curves, you can study the Pisevich table maps. These are there since the 90s that have given rise to they've given a gate impulse to enumerative geometry. But the problem is, even if you look at modular spaces of maps to project this space, so you need to keep the target complexity to minimum. Somehow these modular spaces turn out to be very complicated. In fact, for if you take P4, and that the genus the arbitrary, then they satisfy this law. So this space is very, very similar. And the idea is that from this paper is to exploit the geometry of more singular curves in order to find better, so smooth and irreducible compactification of the minimum pole, which of course has also applications to numerical geometry in the sense that it can find numerical invariance whose meaning is perhaps closer to the count of smooth curves that I would like to keep than ordinary mobility. And then from this line, I'm here to complete the graph with this, and so this work is in G1, and the model construction of particle and singular and we do one in G1. Right. So the third sort of application, which is somewhat similar in favor of what mentioned moduli based on effector. And here we have a very similar problem. So there is a more distant from compactification. So compactification but let's say the most natural description that you can give of this of the differences produces a non-irreducible modular space, and then it is found in the work of David and Luchesky and Von Müller. A condition is found to single out the main component, and it's a sort of analytically favored condition involving this of these differentials, which are both holomorphic and neuromorphic, put together with holomorphic and neuromorphic things. Right, so this compactification is coming. There is already a description of the main component of its explosion, but there is a conjecture due again to random mice. There is a conjectural description of the main component of this moduli space, again, in terms of differential that we send to as a singularity. So, and we have checked this with Luchesky last year in the very special case of hyperpredictive. And also earlier this year, I have postulated a paper on genus 3 singularities that contain some more conjectural relation. So let's say between differentials, mutable differentials, and mutable okay, I'm almost done with my panorama for today. So the fourth application I want to mention is the one that I'm going to talk about essentially, and it's the computation of integral charges of activities. But before talking about my work with Andrea, I want to mention earlier work of Lorenzo. Where they compute the integral charging of MP1. Okay, and perhaps I want to spend the word on their strategy and other strategies that we so far. So let me now start my discussion of integral charging.
Can I ask you a question? What's the conjecture related to the scale integration? What's the conjecture related to the multi-scale compactification?
Yes, let me face it a bit rapidly. Okay. even some, would it be okay if I answer the question at the end?
Sure.
Right. So I want to talk a bit more about that part. Okay, so previously, my pattern is that essentially two sort of techniques have been employed in order to compute intellectual of complex spaces. And also, you should say that the range of moduli spaces whose intellectual is being computed is really limited. It's pretty different topic, and mostly there are two techniques that have been employed. One is basically excision. So what excision? Say you have an open circularity, and say that you understand both the open and the closed complement pretty well. So if you can compute the integral values, you might have to put them together and do the integral value of the by the excision algorithm. So there's a restriction from the open and given by the cycle supported on C. The problem is that these sequences are direct exact, and if you want to have with it and understand the kernel of the map, then we need to compute higher Chow groups. So this is one path that, for example, has been used by Eric Clarkson in the computation of the integral of energy. The other is a technique that comes from providing differentiation. It's sort of similar, so the idea is to understand to compute this the integral ring again by patching, but instead of using excision sequence, there is a sort of direct argument where you can patch the pieces directly if you know that the normal bundle of the closed subset is not a zero device. Okay? So you see, this is typically a problem. So this is a problem in what the Riemann, the Riemann stance, because then the command, the child will be proportional as soon as we go over the dimension of the space. So certainly this doctrine task will be. So what the technique that has been used by the Lorenzo history, among the others, does is you enlarge your moduli space to consider some more singular curves with more automorphisms, and then you perform a computation there where there is hope to apply such a thing. So in this from design, similar curves enter already. So, for example, they studied the integral ring of M to the 1 bar by studying moduli space by admitting cusps in the moduli spaces. Okay, the story that I want to make, that I want to tell is the big difference in style. So what we are going to do is we are going to speak with the name stacks, but we're going to look at several of them, and with the idea that as you go along with your minimum model problem, this makes your model space simpler and simpler. And so you may get to a point where actually you can compute that everything very easily, and then you have to go back to where you started. And if you're lucky, as we are in this case, this is just a sequence of blowups and blowdowns, and so you may perform your computation by a blow for you. So this is in the end a pretty straightforward computation. So the two theorems that I want to present are theorem one is presentation of the number from the representation. Okay, let me say M1n bar has a sequence of weighted go up and down from very simple stack. By which I mean either a weighted projective space or a class n. So this works in the range n less or equal to 6. So for very low number of minors. Then okay, so let me just say okay, maybe I will say in a second. And which is part of this is computation of the integral value of n to pi using this presentation. And I will try to focus on n to pi because it's maybe first slightly more interesting example, and also the last one that we have done so far. So this is the one I try to explain. Let me just mention that this generalizes three facts that we might know. So, well, first of all, might know that if you just look at M11, then we identify with a weighted projective space that is equals. And so by this identification, the computation of integral in forward direction is already in the original paper of Leading Down, where they introduced the integral for quotient stacks. That is the integral of M1, but is polynomial in the lambda class with the relation of 24 number square. So, and already here you see that if you look at integrals or instead you get some more information, and then you get rational, you get this from this 24. So rationally the relation is just lambda square, but actually integrally is lambda square and the multiple and not zero, but just torsion. So in particular, notice that they don't they're not zero or homologically above the dimension of the space.
Could you say very fastly that as one? You say some words about that. What P460?
Why is P460?
Yeah.
I mean, what that speaking it comes from the Weiss's form of you use that to produce this. perhaps you know already that the course formula is P1 by the J by, and this is setting function.
Just something your there looks a lot like an N.
So maybe this anyway, I will talk about that one. Yeah, the second word we want to mention is words like the binding also from a couple of years back. We presents M1 part as a music blow-up of wave 4 and 6 of another projective space. And again, he does it. He did it very explicitly by working with different types of normal forms, and perhaps what I will try to explain in the next half an hour also shed some light on this presentation, and he himself used the presentation to conclude the integration of an and this result to be seen lambda delta with relations delta plus lambda, and again 24 lambda squared. Okay, so you may do this work as a generalization of these new basics. Okay. So what I'm going to do next is explain the geometry of the compactifications introduced by David Smythe and how to use them in order to make this computation. And that's okay. So now is the point where I introduce some new singularities here, and then I will tell you about Smythe's theorem, how you can put them together for alternative compactifications of moduli space of point of the degree. So first of all, I want to do this of these one singularities. This starts with two classical singularities, primary singularities, one of which is already been mentioned, it's the ordinary passage. So the one of the equations quite clear. In the plane where singularity. And the second one is the pattern, so the union of two tangent branches. And the list goes on. There is actually one such singularity for every number of branches. So irreducible components of the normalization, and I'm talking about analytical curves here. And they all need a uniform description for at least three branches, that is the union of n generic lines through the origin but this is occurring not in an as would be more natural, but in an minus 1. So the next example in line is exactly the unit of the two lines inside the plane. And this is also a classical triviality that I present. Okay, so I just presented them as a list, but in fact, as mine two that these are all the similarities of the union. And I'm not telling you what Goethe is, perhaps the model means that these are corresponding and dualizing is actually a line bundle. And I'm not telling you what the use of the similarity is, but you can think of it as the local contribution of the similar point to the use of a projective curve. Okay, but this doesn't matter so much. What I want to explain is that so first of all, again, by the word was mine, these are the singularities that you get by contracting an elliptic and which, let's say, in a generic one parameter time. So for instance, this is an example that I will come back to. Suppose that in a one parameter family, so over this, you have a genus one curve, degenerating to a stable curve that has the genus one core and the stability that is set with 4 margins. And then well, I look at the degeneration where the special fiber has an elliptic bridge, so an elliptic curve that patches the rest of the curve in 2 points. And in this case, for example, this is an example in M1 4, and this so the 4 points need to go from the rational tables. So over the one parameter family, what we do is we can cut this genus one bridge and produce a pattern. Okay, so once you have these similarities and you know how to contract them or replace them with basically once you know the semi-stable tails, semi-stable reduction, then the following definition, which is fine, it's natural. So does the bridge have to have both sides integrally? Yeah, the smoothing parameters must be the same.
But what if there's no? What
if
the
no.
bridge is flat?
Right. In that case, one thing you can do, and this is what happens in this compactification, you can blow up that point. So you take the strict transform, you replace it by a rational notation, just one marking, and then you put contracting. I mean, if you contract directly, then you get cast, but the section will pass through the top. So, okay. So what is the idea? Is that what I'm going to find now is the compactification of spines. The idea is that we want to vary the combinatorial complexity with one singularity. So we allow singularities that are directly and reinforced, which leads that I just presented. But in exchange, we are allowed to request that the combinatorics of the underlying curve is singular. Okay, so what I'm writing, so it's 10, which is between 10 and 10, and then my difference is one of these things of n stable first. You're going to be here. Yeah, thanks. One of the case of curves. So C is a projective curve of infinite genus 1, and it only has so the singularity that we allow are not only nodes as in the Riemann interpretation, but nodes and the singularities that I these here that are called elliptic n 4 points. So n is the number of branches. So we only allow nodes and elliptic n points or L that's between M. But in exchange for this, we are allowed to ask singular combinatorics. So we ask that every subcurve is D, subcurve of identity minus 1. Then this curve intersects the rest of the curve and the marking sections in a high enough number of points. So the number of the linearity of each intersector is 3 minus 2 plus the linearity of markings that lie on the subcurve must be strictly larger than n. Okay, lastly, the finiteness of automorphisms condition that can be also placed combinatorially by saying that there is at least one central point for every branch of an elliptic N4, and at least one branch has at least two. Okay, it doesn't matter so much. There is a entirely combinatorial way of trading it, and basically makes it so that every branch of an elliptic helping point must be independent. Okay, so let me go back to this example. So, okay, this is the stack of n stable curve as defined by point. Then is one of these results is that the moduli case of n stable curve is a proper the number stack over that of so when three tasks and taxons have more automorphism than usually, so those are primes that you should avoid when you work with them. Let me add that N1 and N is moved only for N up to 6. 5. Okay. So this is one caveat and one price that you have to pay for introducing this word singularity. So the thing is, you see, we started with some classical planar singularities, and the derivation of those is easy when understood. But as you go along the list, you get singularities with more and more branches and higher embedding dimension. And then the deformation theory of this curve becomes very complicated, not really well understood. And in particular, the universal deformation is singular as soon as they are fundamentally for right. So the idea way we could integral Chorin is by using this part. In fact, not only integral Chorin of the part, but also of all of Smythe's alternative simplification. And here is one reason why going beyond a certain low number of findings might be hard. These tags can become singular as n grows. On the other hand, if n is at most 6, then all of the alternative compactifications of Smythe are smooth, and so they have integral Chorin.
5 or 6?
So n is less or equal to 5, but n is strictly larger than n, and so we can get up to n equals 6. Okay, I want to go back to this example for just 1 second. So I told you that the Finkelstein's theorem, one of the theorems is that these stacks are proper. In particular, they satisfy the validity criterion. But so what you see here, if you look at this curve with an elliptic bridge, then this genus 1 subcurve has only 2 points of intersection with the rest of the curve. And so this curve is not spherical in the case of Smythe. And the point of the properness result of the validity criterion is exactly that. In a one parameter family, you can replace this genus 1 bridge with a gap, which is sort of singularity that is allowed for n equals 2. So you can okay. One problem with this is that one problem with this is that these contractions only work so well over one parameter basis, but over the whole moduli space, in particular, there are birational maps between these various compactifications because the smooth locus is untouched. It's open density moduli. But typically, these birational maps are not regular, not defined. So the first example is exactly n equals 4. I just want to give you a hint as to why it is the case that they are not tagged. So then on n on one side and n on m are birational. This is because they both have the locus of smooth curves as a dense open, but the map is not regular. It's not what is less 1 and 1. So the case n equals 1 is sort of well known in the field because it dates back to this construction of Schubert. So there is always an act from M1 to 5 and M1 and 1. And if you look back at the definition, M1 and 1, the moduli space of curves with nodes and cusps where elliptic tails are not allowed. And so we know that this is used in the 90s by Schubert, and we call them pseudo-stable. And this in fact is an instance of the first of the classical problem. And then there's these other extreme cases that I don't explain perhaps, but let me just draw the diagram for M14. So we have a direct contraction for from M14 to M141, which replaces, so contracts the locus of the details into the locus of the cusps. And then we have a Baratino map to M142. And we have a method to M142. And that's all. These are the compactifications that the good news is that we know how to solve this map. And in fact, the problem is the one that I alluded to before, namely that these contractions are well defined in one parameter families, but not more generally. And the point for the problem is the way that these similarities so the statement is actually wrong. Perhaps the right thing that I just said is the normalization of these singularities at moduli. It's not the germ of the singularity itself. But let me try to explain. In the case of a Tachnam, the way I like to think about it is the following. If you want to obtain a Tachnam, well, you can look at its semi-normalization or its normalization. Let's say it's semi-normalization. The semi-normalization is just the universal curve that is homomorphic to the one you have. So topologically they're the same, but it's actually different. And it's just a norm. So how can you go back to how from the norm can you construct the Tachnam? But one way to think about it is you have to select tangent direction, which is not from say the step into the node, and then you have to push it down to a point. So the push up of this diagram gives you the Tachnam. But so let me say it again. It works by pinching the tangent direction, net tangent direction in the tangent space of the node. So the point is that this map has moduli. You have to choose the tangent tangent direction. So these moduli can be identified to be the end and can also be compactified to P1 in a natural way that probably I will have time to explain. But anyway, the point is that basically the contraction that you get there over one parameter space does not only depend on the central fiber, but actually depend on the smooth. So if you want to have a contraction defined at the level of modular spaces that we would like to have here, then you have to enhance the modular space with the information parameter for the feedback for the normalization. But it turns out that this is actually really easy to obtain. And in fact, in order to the problematic place here is the locus of the liquid bridges. So the locus of curves on the curve of the form genus 1 curve, then two rational as a very good one. So this is problematic because it's the locus that is one stable but not two stable. And what I'm saying is that in order to resolve this indeterminacy, you're going to have to blow them up. Right. In this case, we call M1 for units. And now it's explained in much larger generality in the paper of Jonathan and Kelly, and then by Smythe in the step-by-step way that we need that from from this space, you actually get the contraction to M1 4. So basically, I'm saying blowing up this codimension 2 locus over it, I get this P1, and I get because that P1 as the moduli space for the contractions to the pattern. So it's exactly the information that I need in order to produce my contraction on the universal curve and then from M1.3 to M1. Okay, so this is essentially Smythe's work. And then in order to do the computation, there's one X impedance that comes from one of the GPU and policy. So they came to it from the point of view of mirror symmetry and A structure, so quite a different place to start. But in the end, the result of their work that we did is that if you look at the last of Smythe's multiplication, so M1 N minus 1, then this means explicit equation. So they describe them extremely explicitly, and in particular for low values of n, it turns out that they have all weighted projective spaces for the time and so let's see. So for n equals 2 before, remember in of the work. And 3 that 1 2 for 4 we have E1 from 1 to 2 and for 5 we have 5 and for 6 we have this kind of
And then description for M111.
What's M111? Yeah, I mean they have explicit equations for all of them, but then they're unintegrated just equations in a weighted projective space. Projective space then becomes the height. Yeah, just mean they have explicit equations, but they become just part of the. So I don't know is the answer, but they do.
Well, I think you convinced me that the corresponds to that space in this moduli here for the singularity is P1, but how do you know you're gonna you have to do weights blow up or
No, it's not on this side. So the gaming space is similarities, it's just always A1 minus 0 to the number of branches minus 1. It's that. And then there's a way of compactifying it by sprouting pretty much in the way that you asked before. That makes it into projected space.
But for the 5 and 6, it's the speed.
So the final compactification we did, but then what I'm going to tell you next is that now we can exploit this description and go back on the tower of compactifications, and all of the maps that are not ordinary blowups are weighted. Okay, I don't have much time left, so let me just use the board that I sort of. I think I had underestimated the amount of time that it is required to write so many relations. So, sorry. Okay. Maybe I should mention one more thing in general. So now that we have this explicit description of these finite compactifications, so basically we can make the following observation. Look at the map from M1 and like before from M1 and M-1 to M1 and M. A generalization of what I explained here tells you that you can just grow up the locus of the unique bridges of, let's say, M bridges. With M, the neighboring points in there. To get word one, and minus top. Well, actually, you can construct the universal curve over this locus and produce an M stable point, so you get the map down here. And now, so this is an ordinary blow up, and this solves the indeterminacy. Now, what I want to say is that when N and the locus of the Nicky-Caron bridges is isomorphic to N1 N and minus 1 times some 0 factors. So let me forget about it. But now we have an identification of this thanks to this theorem with a weighted projective space for low values of n. And so it's tempting to think that actually this is just a weighted block of the same weights, and it actually is. So for n, and that's equal to 5. This is a weighted blow of the weights determined by this theorem of the inequality. And in order to prove it, we use a sort of generalization of Hartley's compactibility in the theorem. That has been proved in the context of weighted blow-ups and smooth the remember sets last year by Arena, Di Lorenzo, Inchiostro, Mahmoud, Obina, Vernice. Anyway, and for this reason, we received in our work characteristic 0 because this is the generality which they have proved, but I'm convinced that it can actually go around this restriction to invest more work into it and not just what we have. Okay, and okay, so basically, this is the end of my talk. This is the tower that we've been looking for. That's what we have until now, and you have an identification now of this with 11111. And so, in particular, Chow generated by the corresponding lambda class, with a relation for lambda to the power 5. And then all of these arrows in the diagram are with the blow-ups in loci GAUS similar curves that can be described inductively. And so by applying the weighted blow-up formula, so there is an ordinary blow-up formula defined on chapter 6, and then there's extension to weighted blow-ups as been proved by Irene. And we just applied repeatedly to go up the tower, and that very simple shouting we go back until we compute the integral of n14 bar which looks a bit like this. I know it's not really technical, but there are 12 generators in the P1, and there are about 100 relations among them, which are mostly quadratic relations, and you get the 4 lambda square, and you get some torsion, some relations that are torsion in degree 3, and so in all of these things, just a repeated application of the blow-up formula that is that where you have to go down instead of up, but this is not hard to see. So the answer was that once the geometry of these alternative compactifications is so well understood, then computing invariants of your moduli space, such as the integral Chow, becomes very easy and very